Hi! In today's video, I'll be going through combinations. Previously, I've already went through what are the basic principles of counting and what are permutations, which are an ordered arrangement of elements. For combinations, it is basically all you want to do is choose the elements, and so ordering within the chosen elements does not matter. You could choose from a set of 1, 2, 3, you can choose 1 and 2 first, or 2 and 1, and they are the same subset, and so they classify themselves as one combination. And so we denote the combination as n choose r with this notation, and it refers to choosing r elements from an n element set. So some nice properties is that choosing r elements is the same as not choosing n minus r elements. For example, you have a set 1, 2, and 3. The number of ways to choose 2 elements is 3 choose 2. And the number of ways to not choose 1 element is 3 choose 1. And these two things are equal. Furthermore, you can see that if we want to permutate and arrange these r elements, it is just going to be r factorial. Since we have exactly r elements now and we want to arrange them, so now you got r choices, r minus 1 all the way to 1. And the total number of ways is r factorial. And then since you previously chosen them, it's from n choose r. And what does this give? It gives an r permutation of n element set, and that for r factorial times the combination is the same as the permutated symbol npr. So that's basically it for combinations. It is just you choose the elements you want in your subset to meet the required number. So let's go through some examples. First, let's give a brief use of multiplication principle in part 1, where we want to ask what's the binary sequence of length 7. And so we draw out the number first. So this could be 1 or 0. So there's 2 choices. The second one also has 2 choices, because it can be 1 or 0, 1 or 0, 1 or 0, all the way to the 7th place. And so the total number of ways using the multiplication principle is 2 times 2 all the way, so it's 2 to the power 7. Next, how many of them contains 3 zeros and 4 ones? Well, if you have 7 slots, you basically need to choose 3 of them to be zeros and 4 of them to be ones. And so you just choose 3, and the other 4 must be ones already. And so it's just 7 choose 3. That's pretty simple. Let's move on to a more complicated example. Now we say that there are 10 boxes arranged in a row, and 7 of them are put into boxes such that they at most hold 1 ball, and no 2 empty boxes are adjacent. So you can imagine that you arrange the 7 balls first, and since they are distinct, that gives us 7 factorial. But you have 10 boxes, means you have to put 3 empty boxes inside the slots of the 10 balls. And so you have now 8 possible choices, and you just need to choose 3 of them to put these identical empty boxes. And so it's 8 choose 3. The reason why we want to slot them is again because no 2 empty boxes are adjacent to one another. Moving on, let's see one more example before we move on to proving techniques. In our example, we now want to have at least 1 female student to be selected to form a group of 7 with 6 females and 8 males in total. So how many ways to form the community, since this is showing at least one female, we can take the complement as it will reduce the number of counting that we need to do. We take the total number of ways first to choose 7 people, which is 14 choose 7, and then we minus off the event that no female student is chosen, in which case the 7 people all were from males, and then that will be just 8 choose 7. Next, to take up 7 different posts in the community means we want to arrange these 7 people in a linear order. And so you just need to take the number of people ways chosen times the permutation of 7 factorial. Lastly, now you know that there's only 3 different positions, and so out of the total number of combinations, you just need to permute them 7p3. And that's all for this question. As you can see, choosing is a very simple task, and you just need to know what are the constraints required so that you can choose appropriately. Let's move on to how we can use combinations to prove algebraic identities. For the first one, it's one of the more classic examples where n choose r is actually the same as n minus 1 choose r plus n minus 1 choose r minus 1. While you can work out the algebra and just expand it and show that they are equal, left hand side equals to right hand side, another way is to use a combinatorics proof, which is what I'm going to show you. So on our left hand side, it is n choose r. And so we take an n element set and we choose r of them, and that gives us the left hand side. So now how do we choose r of them? There are many different ways, but let's consider this way, where the first element is chosen in your subset. And so you only left to choose r minus 1 from the n minus 1 objects, and so it gives us n minus 1 choose r minus 1. The complement of it is now that element 1 is not chosen in your subset, and so you still need to choose r elements from the n minus 1 elements remaining. And thus, these two cases covers the whole thing, and hence, the total number of ways is just adding them together by the addition principle, and it will equal to your left hand side. Hence, you can see we didn't need to expand out any of the combinations and do any algebra, and will result in showing this identity. Another classic example would be n choose m times m choose r is the same as n choose r times n minus r choose m minus r. How do we think about it? Well, let's say you have n members in a community, and you want to form a group of m with r of them being a row. Well, then you just need to choose the first m people from the n, and then from the m people you choose r of them to take up positions. But you can also count them in another way, where you choose r of them to be the positions first, and then now you choose the remaining people to fill up the rest of the non-position people, so the normal members. And so you can see how counting in two different ways resulting in the same problem leads us to prove identities. We'll move on to the last identity, which is one of the more complicated ones, so follow along closely. Firstly, our left hand side is a purely algebraic structure of a summation of the square of the terms, and we'll show that it can equal to the choices on the right. So let's see what our right hand side says. Our right hand side says that we are choosing from an n plus 1 element set, and so we consider the n plus 1 element set. Next, we consider a subset of the ordered tuple where x, y, and z come from this n plus 1 element set, and then x must be less than z and y must be less than z. And so this just means z is the maximum element and x and y cannot equal to z. And so, what is the total number of elements in this T now? Well, if you break them into cases now, if Z is the 1, then X and Y has no solution, so that results in 0 ways to get this inside T. Now if Z is 2, X and Y can only be 1 and they must equal each other, and so the total number of ways in this event is 1. If Z is 3, X and Y got 2 choices. They can be 1 or 2. Y can also be 1 or 2. By the multiplication is 2 times 2, which is 4. And you can see this pattern repeating, and when you have n plus 1 for Z, X and Y can take both n and n, and so it's m squared choices. And hence, the total number of elements in T is just the summation of this, which is our left hand side. So now we need to consider another way of counting. This way of counting is saying whether X and Y are the same or X and Y are not the same. If X and Y are not the same, it means from our n element set, we can choose 3 of them as they will all be distinct. And then, they never say whether X and Y, who is larger than who. And so you need times 2, because in the first case, X is larger than Y, and in the second case, X is less than Y. Now, in the next case where X and Y is equal, then you only need to choose 2 elements, the larger of them being Z. The other one will be both X and Y. And so you can see now our left hand side equals to this right hand side expression. As you can see, combinations help prove many algebraic identities, which can be useful later on in the studies in other areas. We also use combinations to find the number of ways we can choose elements from a given set and create the subset. Combinations is very encountered widely in binomial theorems and multinomial theorems, which we'll do in the next video. Thank you for listening, and I hope you have enjoyed this video. Please feel free to like, share and subscribe, and do let us know of any other content that you wish for us to do. Thank you.